Okay, testing. So let's go to ArcGIS Pro. We will start with basic Lambda skills using Baltimore, Maryland, and data. Um, for LiDAR data, I in my memory that I didn't use a lot, um, at least not heavily used. It's a good chance for me to practice again. And there is another book. This book author have, I think, let's see, working with LiDAR data, and I will pull it out here. Book. Hmm. This is interesting. LiDAR for Dummies. The dummy book is really neat. Wow, that's not everything. That's really a short book. LiDAR data. Okay, LiDAR 101. Learn to speak LiDAR. Okay, that's some of the data and information. It's a good book. Alright. I'm gonna save it. I like it. So okay, and I have a lot of dummy book. So Esri, working with LiDAR data. This is just, I think it will be a journal article, let's see, or a manual thing. Oh, this is for archaeologists, which is very nice. Okay. Outline the data collected. I think it's a little book, and they have some of the manual here. Oh, cool. This is really nice. Okay. For archaeologists, if you are interested in, we can just. Oh, there is another book. Making decisions. Let's see what Israel have. That similarly we're going to produce. Okay. Um, working. Oh, I think this is the book. Yeah, that's the book. Using GIS and LiDAR data. It's the same author. Let's see if it is available. Still available. Okay, yeah, it is still available. Okay. That's what we're gonna to work today. I'm going to open a blank. So one of the first data tasks we will explore the properties and statistics of an LAS dataset and conduct an interactive surface analysis and identify classes. We will classify terms and generate elevation, slope, aspect, and contour visualized in 3D and create a layout of a LAS dataset. One of the first tasks for a GIS department using LiDAR data is to understand the functions provided in the ArcGIS Pro interface. As an intern to the GIS department, the task is to create an exercise that provides information about the Appearance tab. In addition to the Appearance tab, and we will provide instructions about deriving pertinent statistics and visualization the data set in 3D and creating 3D layout for an example LAS dataset. An LAS dataset stores references to one or more LAS files on disk, as well as to additional surface features. An LAS file is an industry standard binary format for storing airborne LiDAR data. The deliverables, we summarize the workload here. The first one is to layout of the Baltimore dataset with an explanation of the study area. And the second one is a written report explaining basic LiDAR information and statistics with visual examples of ArcGIS Pro functions. Number 3, a 3D scene to view LiDAR data in 3 dimensions. Number 4 is 3D layout to export as a printable PDF. We already have the data, and I think I just create a folder and everything, and I will just extract the folder, and we will see if it worked that way. The same way I go to making spatial decision folder, and this one I will just say Baltimore. Okay, Baltimore, click OK. And add a new map for sure. Okay, add a new map. And the same way I'm gonna go to analysis and tools, extract packages. Okay. Extract package. I don't see package. Package. Okay, right here. Data management tool. And it's in my download folder. Click open. An output folder for sure that I want my documents in my folder. Making spatial decision and run. Okay, so now let's get connection to the folder and see if the data is there. Click OK. There, folder connection added. And we expand the folder, and let's see, Baltimore. Baltimore underscore data. Right here. Okay, so now we have the data. Baltimore underscore data. Okay, layers. Okay, Baltimore City, buildings, highways, and water. Now I'm going to right click on layers and then add to current map. Then when we added data to the map, ArcGIS Pro creates layers for each data source and the layer reference the actual source data and can contain many different display properties. So for example, we can change the colors of the layer and how they are symbolized and the layer name and labels. So let's start it. I have highways, buildings, and water. Buildings, water, Baltimore City. And it's a good time for us to familiarize the data. I'm gonna make this color is no color that we can see through all the data. Or I can just, that's fine. Okay, then I'm going to save my project. And then on the contents pane, we're going to look at the spatial property coordinate system, and let's stay plain Maryland, Phipps 1900. So go to highways and go to source and the spatial reference. Okay, so our spatial reference will be in a NAD 1983 State Plain, Maryland, Phipps 1900 feet. And next we will set the environment settings, and we look at the coordinate system for geoprocessing to the same coordinate system as the data frame or first layer, because this projected coordinate system most accurately preserves measurements within the localized area. And in the catalog pane, we select the project tab and expand database and identify Baltimore results geodatabase. I'm going to environment. So this database will store all of the produced data files. So which is right here. Gonna cancel it first and I will bring it back, which is Baltimore geodatabase environment. So everything set that and go to Maryland Phipps 1900. Okay. Maryland Phipps 1900. Okay. So we finish everything. Click OK. And we said, oh, the extent. I need to set the extent. Extent I have to send is Baltimore City. Okay. I forgot to do this, which is the processing extent that I set it to the as specified below, which is the Baltimore City. Finally, we could create a process summary. A process summary lists the steps we need to do for the analysis. So the summary will allow us to or others to reproduce the work. We suggest using a simple text document for the process summary, adding to the summary as we work to avoid forgetting any steps. The next list shows an example of the first few entries in a process summary. We already extracted the project package, and now we're going to produce a map of Baltimore City, create an LISD dataset, and we will examine the LiDAR data. Cool. It will be beautiful, I promise, okay? The analysis, once we have obtained the data and set the environments, we are ready to begin the analysis and complete the data displays we need. For this module, we have been asked to examine a dataset, create a 3D sim, and publish the same. The first one, deliverable one, a layout of the Baltimore dataset with an explanation of the study area, produce a basic Baltimore map. In the contents pane, which is right here, we will click the square under Baltimore City and choose extend transparent, which I did, and right click the square under water, so water, which is here, and change to medium gray. No, to change it into a dark blue, ultra blue. Excuse me. And the square, right click the square under buildings and change it to dark brown. So dark brown. And click, oh, buildings, let's see, buildings, medium gray. Okay, medium gray, sorry. Medium gray. And highways, it will be brown, dark brown. Base map, go back to map. We will change the base map to imagery with labels. First step we're going to create is that's the Baltimore, and this is the water, river, okay, and this is the city extent. And we can create a LAS dataset on the analysis tab and go to tools. So for tools, we will create LAS dataset. LAS dataset, LAS to raster LAS. There are so many tools. Create LAS dataset, data management tool. Input. So for input in Baltimore result data, we go to input feature output dataset. output dataset, we will type in, let's see, cannot put in our, that's weird. We will check all these. Okay, select compute statistics and store relative path. In Baltimore, results, data, we have to input a file. So we go to desktop, in here, and in here, and in here. Go to results. Where is results? I think it's in common data, user data. Yeah, user data, Baltimore. That's the input file, MD, and the Baltimore 2008 1S1W LAS, and click open. And output already identified for us. Output, this is MD, I think I just leave it as default. Coordinate system, I have it already, and create PJ. Create, where is the create? Okay, create PRJ to LAS file, no LAS file, and we select compute statistic and store relative path. Okay, running this geoprocessing tool create LAS dataset, we have the input layer and output LAS dataset. I just use the default name and we'll leave here M blank. The option is blank. We do not have an input for there. So now our coordinate system, NAD 1983, State Plane, Maryland, FIPS 1900, and feet. No LAS file, and compute statistics and store relative path, and click run. There, and it says completed successfully. Then we will, everything is here, okay? And where is, okay, so now our MD Baltimore 2008, this file automatically add to the layer, and I'm gonna close this out and right click on here and zoom to layer. Okay, so now we can see some colorful stuff, and I'm gonna turn off the building. And it's very beautiful. And I'm going to move this to on top. Word boundaries and places. Okay, I think that's for the word imagery. Okay. I have to put on top so I can see those labels. And what is the range of elevation? So let's see, what is the range of elevation? Then the range is you use this 2 minus the other one. So we have, let's see, we have a 416.86 kind of U plus 228.87. So you do a math that we have 3 and 7 and then 5 and then 4 and then 645.73. That's our range. Okay, we could also check, let me go to the folder real quick and double check with the data. Okay, so we are on chapter 7. Chapter 7. Okay, so yeah, you could calculate it and you do not have to. So which is right here. Negative 228.87. So that's the range. Okay, range you could calculate it from which number to which number. And we can continue to zoom in the dataset until we see a series of points. Yeah, I do see a series of points. And we will click the value section to activate the symbology pane and move the symbol scale closer to minimum. So let's see. Right click on this layer and go to symbology. Symbology, we have elevation, and I'm going to drag it to a little bit more minimum. And we can now see the individual LiDAR points. So yeah, that's the point. And we can also see the collection swath of the plane. Yeah, you can see right here, and it has more. Go back and forth, go back and forth, go back and forth. And using the imagery with a label base map and turn this layer on and off, and contents pane describe the study area quadrant, and use the University of Maryland Oriole Park and Camden Yards and the B&O Railroads Museum as points of interest. Let me turn on and off, on and off. Very interesting. And before we begin any analysis, it helps us to know the basic facts of the dataset. Metadata was downloaded from the U.S. Geologic Survey along with the LAS data and can be accessed in Common Data User Data as MD Baltimore 2008, which is our input data. It is 1s1w.mxl. However, there are easier ways to explore the metadata. We can right-click on this layer and explore layer properties. So I'm going to click layer properties, which is right here. And we will complete the next chart. We will click several of the tabs, including the spatial reference tab, projected coordinate system, which is spatial reference, that we can see the spatial references right here, and vertical unit. Let's look for vertical units. Vertical units should be NAVD. Click OK. Let's see. Property again. Okay, I can do is just view metadata. Preview. So now we are back on scale range extend. It didn't record everything yet. Let's go back to the not this map, map 1. I think I must be click it twice. Right click on it again. Okay. Source. Extend. Spatial reference. The vertical. Let's see, where's the vertical? I don't see the vertical yet. 1880A. That's a good one. Okay, I don't see the vertical yet. And then we will find the load date. Load date. I don't see the load date neither. Okay, and then the tie area. Load date, tie area. Okay, load date, tie area. Spatial reference, it should be all in here. Let me expand a little bit more. And I don't see nothing. Tie area and classification code. Nope, I don't see classification code. And point spacing. And I still need to find this point spacing. That's really interesting. No. Okay. This is the file name. I'm going to right click on it, click copy, and we're going to bring Python window. Click OK first. I'm going to bring Python window. So Python window, and I'm going to argpy dot describe, and I'm going to put this file name and dot point spacing. Argpy describe. I think something wrong with with the scripting. Import argpy and argpy describe. Dot point spacing. There. So now I have to import argpy first, and then now the point spacing is showing up, and let's Control Z. Doesn't like it, and I don't want this. Let's see. Okay. And I'm recording this, and dot I want Thai area. Thai area does not exist. Okay. At least this is this working fine. Okay, but here I still do not see the other data. We need to click several of the tabs. The other tab, including, let's click the tab again. Filter. Can I expand this? I don't think so. Cached, elevation, source, extend, and spatial reference. That's all I have it here. And it didn't tell us some of this information. We know the data, okay. And the general, it didn't have anything. Surface constraint, nope. Nothing here, and everything is here, and I don't see the vertical. Oh, vertical units. Okay, I see vertical units. Vertical unit is US feet. Okay, US feet. It's a little different and didn't include the load date. Linear unit, it has linear unit. Okay, it's good to explore this data and look around. So the only data that we cannot find from this window is the point spacing. Point spacing, which we used via Python window. I'm gonna drag it this side. So, okay. Point spacing. Point spacing determines the resolution of derived graded point products. The point spacing that is used in calculations is an average because point spacing is not consistent with the data set. And for example, the tiles that have large bodies of water typically have a large average point spacing because of the large empty spaces. And we find this point spacing on the analysis tab. We click Python, and which I already did. You have to import ArcPy first, and I think maybe some of the tools, if I type import ArcPy, that could run. And here the question asks, how does point spacing determines the resolution of the derived graded products? How would the horizontal resolution of point spacing of a data affect the resolution of ground surface feature? We have to write a brief paragraph about the data, including the number of points, vertical units, spatial reference, and classification nodes and return values. I think which are all here. There are 300. Let's look around it. No, 3,556,042 points with the vertical units of feet. And the spatial reference is right here. Spatial reference is NAD 1983 State Plane, Maryland, Phipps 1900 feet. The classification nodes are class 1 unassigned. Class 1, let's see, where is class 1 unassigned? And then class 2, ground. I still need to look. The classification nodes, okay. Okay, right here. Classification code. 1, we didn't have it unassigned, and number 2 is ground. Number 6 is building. Number 7 is low noise. Number 12, overlap reserved. And number 18, high noise or outliers. So that's something we need to write it down. Something very interesting to point it out. So, filter thing, and if we cannot find any thing, classification codes. Okay, I find it. Tie area. I don't see the tie area, which is in. Okay, I found this. It's a little different, which is LAS filter. Point spacing, we don't see point spacing. 1 square per mile load date. Vertical units, I think cache elevation. I still have to find it. Where is the load date? Okay, right click on it and view metadata. There are no credits, nothing. Write it here. That's weird. Nothing recorded nicely. And we use the Python to get some of the information, okay? Close it out. Right click on it again. Let's see, edit metadata, because this file is... I guess now they updated, we cannot see the date. There is no source there. Extend and nothing is here, okay. That's fine, okay. And we have the fill rate, okay. And we will do next step, we will deliverable to a written report explaining basic liner information and statistics with visual examples of ArcGIS Pro functions. When we click the LAS dataset, 3 tabs become available on the ribbon. Okay, which is right here, appearance, data, and classification. When we click here, and the 3 tabs become available, okay? Each tab has a different functionality. Each tab has a different functionality. We can investigate the appearance tab in this. So the appearance tab point symbology, From the Appearance tab, we have access to the basic functionality needed to alter the display of the LAS dataset. The Symbology menu quickly changes the symbology of an LAS dataset between common point and surface symbologies. The appearance of the LAS dataset automatically changes with each selection from the menu. On the Contents pane, we have this feature. We will select on it and we go to Symbology, Appearance, Symbology. Click Symbology, that there are some options, and symbolize the layer using points. Okay. Symbology, symbolize using points right here. We have elevation and make screen capture in the explanation of the Symbology elevation class and return. Okay. The elevation symbologies points based on elevation value use a color ramp. And the metadata tells us that classification nodes in the LAS data set are 2, 6, 7, 12, and 8. I would just do classification. And then we have everything, okay? 2, 6, 7, 12, and 18. And we have one word code. Let's see, the blue. Let me zoom out a little bit. Because right now I don't see the blue. What do the strip blue turning north or south have identified the colors that represent buildings, ground, and overlay? The code do the strip blue running north to south. Okay, running north to south. My color ramp, I didn't show the color ramp. And we will return some symbolize LAS data point by the LiDAR pulse. Returning number, LiDAR system can capture first, second, third, and a last return from a single pulse. Multiple returns usually indicate multiple reflective surfaces such as a tree canopy. So the return number we have all here. And how many returns are there? And what do they represent? It's all here. The Appearance tab. Now we're going to look at the Appearance tab that we can change the color ramp there, but I don't think right now it's necessary. And we will play around with this, okay? The first part we're going to do in our LiDAR 3D is that's what we're going to create different colors to represent different elevation. I think it's a little weird, but and the surface symbology displays the LAS dataset as a team-based surface. The surface symbology displays the LAS data as a team-based surface, and the four most common surface models are elevation, aspect, slope, and contour. A team is triangulated irregular network is rendered to display the LAS dataset. Once a selection is made, the changes apply to the LAS dataset. Now I'm selecting this feature and I'm going to Symbology Gallery and display the layer using a surface. We could do surface. Okay, let's see, where is surface? This is contour points. Symbology Gallery. Okay, I'm gonna go to Symbology. We will have surface, elevation surface. Okay, elevation, we already, okay, let's do elevation, okay. Okay, this is elevation. We will do, we will explore elevation, slope, and aspect individually. So now, the first is elevation. The three structures listed next are interesting representations of surfaces. For elevation, and I have elevation, and we will choose the elevation method. Choose area park at yards, and for slope, for elevation method. I'm not quite sure this. The area I'm not familiar with. Let's see. Where did it go? There, it's just rendering. Okay, and for slope, I will do building. Let's do slope. This is slope. And aspect, we will choose the BOB Railroad Museum. And we will make the same screen capture to use the explanation for each of the three surface, elevation, slope, and aspect. Okay. And we will describe the display looks using the team data structure. What structure can we identify from the previous image, and why these structures easily identifiable. So the team surface slope identified here is slope. Identify the gradient of the rate of exchange in the z values. When we use the team with aspect values, aspect is the direction of a particular feature is facing. Express it in positive degrees from 0 to 359.9, with a 0 representing north and 108 representing south. Okay, so let's see aspect. Okay, so now we can see the aspect. And what are the surfaces showing the slope and aspect as displays? So, and appearance tab using line symbology. Contours are line. We could do contours. Draw contours. And this is the contours. And we can also choose interval as 20. Contour interval. Let me go down here and go just contour. Okay. Contour index factor. I can do 20. It's rendering. And I'm going to uncheck this. And there. We could change the color and compare a little bit. I don't want to see those labels. And make screen capture to use the explanation of the contour lines, and what do contour represents means they have the same height. Okay, they have the same height within this area. And we will return to the elevation point based symbol in the gallery. I'm gonna go back to elevation. Symbology elevation. Okay. And appearance tab full resolution. We will talk about this. So the appearance tab full resolution, typically the LAS points are displayed as a themed representation of the full resolution point set. The appearance tab controls the LAS dataset layers, drawing, behavior, and point thinning. The point thinning group controls the resolution of the LAS dataset. We can see that the point density has been thinned to halfway between minimum and maximum, and we select this feature in the Contents pane. On the Appearance tab and Full Resolution, we will follow this guideline. Appearance tab, Full Resolution, Point Thinning. Okay, Full Resolution, we have Auto, and increase the density of max and observe what happens to the point display. And going to zoom in and I'm going to drag it to maximum. Display limits. And then I'm going to change this to 500,123. Click enter. Take a long time. Yeah, we see more details. Yeah, we see more details and more realistic. And you can see those bump compared to previous. That's very interesting. Okay, and by changing the full resolution and the display limits, that the 3D it shows a lot different. The 3D could be a little difficult to understand. It's very easy procedure. It just how would you interpret the visualization? It could be a challenge. We will have to continue again. Okay, this is for Baltimore. And once we finish Baltimore, I think next time we will do a San Francisco LiDAR 3D. San Francisco LiDAR 3D could be very interesting as well. And we have to finish the Baltimore and we will do another one for the LiDAR. Okay, see you next time.